Hello, and welcome to the bonus video of day 16. Sorry, not day 16, day 12. I think this is the first bonus video I've ever made. And I'll go over BFS, or breadth first search. I'm going to mainly focus on how I implement it in Python, as opposed to the actual algorithm. And hopefully it's just going to give you a pretty quick, but clear overview on roughly what the algorithm is and how I'd implement it, to give you a place to start off at. And hopefully work on and develop it further to try and solve today's puzzle. But anyway, yeah, I'll try and make this video nice and short, under 10 minutes hopefully. So first off, we'll start with what BFS is. So it stands for breadth first search, and it's a graph algorithm, which means it basically is used to solve something in a graph. And specifically, it's used to find a path from the start to the end of a graph. So you see here, this is what I've got, is a graph. And a graph in computer science or programming is not the same as you may find a graph in maths, which has like an axis and coordinates. That's really what we call a Cartesian plane. A real graph is this, and it's essentially just a load of nodes, and the nodes are just these circles. So a load of these points and paths, and the paths are the lines that connect the nodes. So you can kind of think of it as a sort of maze thing, or like a path somewhere, because you have all of these places you can be, and you can go to them by using any of these paths to get there. So in reality, it's just some sort of thing, right? And this graph can really be anything. So in today's puzzle, you saw it was just a grid, and so each number in the grid would be a node, and each pair of adjacent nodes would have like a path in between them. Because really, a graph is anything. Like, it really is just this. For example, this is a random example of a graph. It's points that are connected. That's literally it. And yeah, the objective is to get from a start point or start node to an end node. And here I've just taken this random graph I found on the internet. And I'm saying I'm going to start at this position called 0 and go to the end position, which is the number 7. And the task is to get there in the fewest number of steps possible. And we're just going to say each step is a path, right? So for example, you could go to 7 by doing this path. But like a fast way to do it would be to follow this blue path. And so like the aim of our program in this example is to try and find the blue path, the fastest path, to get from our start to the end. And that's what a graph is. That's what BFS is, fundamentally. It's trying to find the fastest route by distance to get from the start to the end. And this only works for unweighted graphs. So like we're assuming that all of these paths are the same distance, right? They all like unit 1 distance, for example. But you could get a problem where each of these paths has their own value. It's like this path may be distance 10, 5. This path may be distance 10. This path may be distance 20. That's a harder problem for another day. So right now we're just going to cover the BFS, the basic BFS, where we assume each of these paths has the same length. Right. So what is the BFS algorithm? There are loads of cool visualizations out there, but essentially what you're doing is you start your start point, which is going to be 0 here. And then you expand outwards. So on the next stage you expand to 1 away from your start point, and then on the next step you expand from 1 away from that. So you look at each of these blue layers, it'll be like, what's 1 away from that? That's going to be 2. Which nodes are 1 away from this 3? That's going to be 7, that's going to be 4. And you use this idea of starting at the start, and then branching out to all of the adjacent nodes. That's what we've done in blue. And once you branch out to all the adjacent nodes, you branch out to all of those adjacent nodes. And that's what we've done in green. So that's the order in which things would occur in. So it'd be like 1, 2, and 3. Like these are color coded. And you can kind of see why it's called breadth first search, because you're like going outwards, right? And that's how you search in your graph. Because you're trying to search from your start position to the end position, and you're trying to find the end position. And because in this case we're trying to find the fastest way, we can use breadth, because breadth prioritizes the amount of paths you've gone down, right? Because it checks these blue ones before it checks the green ones. So it checks 1 path away, and then once you've checked 1 path away, you're going to check 2 paths away. And then after you check 2 paths away, well, you've already found your answer, which is 7, which is here. So you're probably going to stop checking at that point. The idea is you kind of go down the graph, and therefore you prioritize steps, essentially. I probably didn't explain that too well. There are loads of videos and articles out there to explain it. I'm more here to show you my implementation. So now we know what a graph is. let's look at my implementation. Right, so my implementation of a graph is a bit different to many people. There are still some people on the internet that use my implementation, but it's much rarer to see the way I do it, especially in Python. Most people use like classes and things like that. I think my implementation is better because it's easier to understand and faster to program, and it's really versatile. So what I'm showing you today is really the basics, the fundamental, the base of a BFS. And like once you truly understand it, spend some time looking at my code afterwards, trying to understand what it actually does. And from there you can adapt it and you can do all sorts of crazy things with it, like solve today's puzzle. You can do all sorts of crazy things with it. And that's why it's really important to understand the basics of a BFS. So here, this is my graph. Let me just name that better. So you see my graph in Python, I just store it as a dictionary. I just separated it on multiple lines to make it clear. But what I have is each node in my graph from earlier, each node here, each circle has is a what's it called? Is a key. So I've nodes named from 0 to 7, so they're all keys. And then the value of each of these nodes is all the connected nodes. So you see here in 0, the value is a list 1 and 3. And if you go back to my graph, you can see from node 0, where can we go? We can go to 1 and we can go to 3. That's essentially what this representation is. It's saying from any given node, which are these things on the side, which other nodes can I go to directly in one step? So which node is 0 connected to? It's connected to these two. Which nodes is 1 connected to? It's connected to these two. Which nodes is 2 connected to? It's connected to just one node. And you go and so on. And obviously you kind of have repeats, like 0 here is connected to 1, but 1 here is also connected to 0. So essentially this is how you format the graph, or how I format the graph of my algorithm. You have your nodes here, and everything they're connected to in a list as the value in the dictionary. Hopefully that made sense. Right, so for the actual graph, one thing you probably want to import is dec. Dec just stands for double-ended queue. Like that's what double E ended, and then K just stands for queue. And it's basically a list. Like it literally is just a list. But we'll see why we use a dec instead of a list later on. Right, so what's our starting position? Our starting is 0. Let's just turn that into a variable. Where do we want to go? Our destination or our goal is 7, I think. Yeah, we start at 0 and we want to get to 7. That's what we'll call those variables there. Right, and now to make our actual queue. Let's just name it queue. That's the queue. And a queue is literally just a list, right? But to turn this into a dec, what we have to do is we have to put brackets around it and then put the word dec in front of it. So dec is just like any casting command, you know, like how tuple would work, tuple command, how the list command would work, how the int command would work. That's what the dec command is. And so we're converting this list into a dec. And in the list, what do we want? Well, the way I like to think of it is we have a state. So our initial state is really just the position, our current node. So our current node is 0, and how many paths have we taken? We've taken 0. And your state can really be anything you decide. As long as it's consistent and it works in your given program, it can be anything. So what our state in this case is going to be current node, and then the second value is going to be steps taken. So obviously we start at node 0, that's just our starting position. And then we haven't moved anywhere, like right at the beginning of the code, we haven't moved anywhere. So we've taken 0 steps. And yeah, I just think of everything within this tuple as a state. It's like our current state. What are we doing in this current moment? Well, we're at the start and we've moved nowhere. And the idea is that you keep adding to this queue. You keep adding more and more states to this queue. So maybe you move to 1 and you've therefore taken 1 step. Maybe you've moved to 5 and you've taken, 4 steps. And all of these tuples are kind of states. That's the way I think about it. And each state represents a different thing you're doing, or like a different position you're at. I mean, compared to our diagram, each state just represents like how far you are down the graph, how far you've explored, and where you currently are. So at the start, we obviously only have 1 state because we haven't really done anything. This is just our starting position. And then you also need a visited set. I'm just using set here because sets are faster, right? And I'll explain that a bit more later. But visited set, this is just because you don't want to visit the same node twice, right? That's just inefficient. There's no really functional purpose other than saying it's inefficient. Because if you visited 3, for example, what path could be 0 and 3. or it could be 0, 3, 0, 3. But obviously you both end up at the same node, so what's the point of having the second one? So you're just taking like 2 extra steps to end at the exact same node. So what we're saying is, if you've already reached a node, then there's no point continuing. Like, you've already been there, you've already seen it, you've already explored it. There's no point going back there. And that's what this visited set's going to be used for. So I mean, at the start, we're just going to assume we visited nowhere, because we haven't really. Right, and now this is like the real algorithm. So we're going to do while queue. This really just means while there's something in queue. So queue is our queue, and while there are states to check. So while there's something in here, then we continue this algorithm. So whilst there are states to check, we need to check them. Right, so we then have to extract the state. So let's do position and steps equal queue.popleft. So what we're doing here is we're popping from the left side of the queue. So you know in Python you probably heard of the list.pop command, which pops from the end. You know, pop left is just the equivalent of doing that. But pop left only works on a deck. And that's why we're using a deck, because, you know, you could use a list and use this command instead, but decks are fast. And that's really the only reason we're using a deck. It's faster, because popping the first item in a list in Python is really inefficient. But if you pop the first item in a deck, it does the same thing, but it's so much faster, just because of the way Python is structured. And the reason we use a deck is just for this runtime speed gain. It's faster to run. But I mean, you can like remove the deck, you can do everything with a list, and just replace this pop with a pop 0. Same thing, just on a massive graph, it'll run slower. That's why you should tend to use decks and pop left. So yeah, we're taking the leftmost state that we have to check, and we're just taking the values of it. So we're saying the first value is position, and so like that's our current node here. And the second value we're taking is steps, the amount of steps you've taken so far. And so at the start, pos will just be equal to the variable start, which is 0, and steps here will be equal to 0, because that's what we defined it in our first state. And you know, as we're checking the state, we want to remove it. So that's what the pop bit actually does. Like, we're removing it from the queue because we're checking a state. We don't need to check it ever again, so we're going to remove it. And now we're going to go through the checking process. So first off, you want to check if your current position is actually the answer. So if you're at the end, then you probably want to print the amount of steps you've taken so far, and then break. So you're breaking out of this entire algorithm, right? Because you've reached the end. That's what you check here. You reach the end, and therefore you're breaking. And you also want to print your answer, which is just steps, the amount of steps it takes to reach your destination. Right, the next thing you want to do is check if you've already been in that location. So pause in visited, continue. Because if you've already visited a node, as I said earlier, there's no point checking it again. Like, you've already checked it in some capacity, so there's no point checking it again. And this is the reason we use a set, because a set is faster to check something in it. So like, if visited was a list, this command would take longer to run. Because it's a set, this command takes less time to run. So really, these are just runtime optimizations in Python. Nothing really functional, it just makes the program faster to run. And again, if you have a massive graph, you're going to see that difference in like minutes sometimes. Like, it's literally minutes and minutes faster if you have a big graph. That's why we use a set. A set is just faster. Obviously, a set can't do everything a list can do, but we don't need a set to do everything a list can do in this case. That's why a set is perfectly fine. A set is really useful, basically, if you want to check if something isn't something else. If you're ever checking, is this item in a list? It's probably better to use a set, because a set is just faster at checking that. Okay, and if it is in the list, then you kind of want to discard your current node. You're saying, I already checked this, let's just continue. And what the continue command word does is it skips back to the start of the loop and continues from here. So that means everything after there, so like everything here is going to be ignored in the cycle with the word continue. Because now we're going to get to the point where we actually check the node. But before we do that, we want to add our current node to visited, just by doing that. So now you're just saying, okay, I'm about to check my current node, and so I'm going to add that to visited just to ensure I don't ever check it again. Because obviously visited starts off empty, and if you keep it empty, like, this command's never going to return true. So you just need to add on as you check nodes. You're saying, okay, I visited this node. Let me ensure I don't visit it again. And just the syntax to do that with a set is .add, as opposed to a list, which would be .append. We're using a set, so it's .add. Right, so now it's the actual algorithm. At this point, we now want to go through and check all of the adjacent nodes. So the way we're going to do that is we're going to be for node in graph pos. And you should look back to the graph. We start off at position 0. So now we're going to go through this list. That's what the for loop does. It just goes through that list. But generally speaking, the for loop will go through all of the adjacent nodes of a given node. And that's what the for loop here does. So we're saying to all the adjacent nodes, to all the nodes you can travel to from where you currently are, let's do something. And what that something is to your queue, you're appending a new state. So the new state is going to be your new node, which is now called node, and the steps taken, which is steps plus 1. And what this essentially says is, so I mean, this is our state, this tuple, and that's the state we're going to add on to the queue, because like we're now going to be in a new location with a new set of variables, new amount of steps, new node, and that's a new state we need to check. And like the new node we're going to be is just this node in the for loop, because we're iterating through all the adjacent nodes, and the steps is going to be just one more than the current step, because to move from your current node to this node, you have to move one step because you're moving to the adjacent node. So you're moving one step. So to whatever steps is before, you just need to add one because you're moving one position to get to your current node. And so what this bit essentially does is it looks at where you currently are. Let's say you're at 0, and it goes through all of the nodes you can go to, which are one step away. So that's 1 and that's 3. And then it adds these two states to your queue, which you're now going to check. And that is literally the code. And so in theory, if we run that, Python 3 day 16 bonus. Oops, I named this day 16 as well. Got my days messed up. But the answer is 2, and let's check if that's correct. What's the shortest amount of steps it takes to get from 0 to 7? And yeah, the answer is 2, because we can go down here and then up here. And that's essentially what our code has done, is found the correct solution. Like, it could very much have gone like down 1, 2, 3, 4, 5, 6. It hasn't done that though, it's gone down the fast way, which is this 1 and then 2. And the way our code's done that is by looking at these highlighted numbers. Look, we go down one path first, one step, then we go down the second step. And you've noticed that on the second step we arrive here, and the code's recognize that and be like, okay, I find my destination, I'm breaking out, this is the answer. And I've done it in 2 steps. So that's what the code does. Hopefully that made a bit of sense, and I'm now just going to generalize the code for you, and hopefully you'll be able to apply this idea, this fundamental base structure of a BFS to any graph you have moving forward. So here you're making the graph, which is a dictionary, and then every node has a key, and the value is a list of every node that you can travel to from your current node. So just a list of all the adjacent nodes. And here you just want to import the queue. You always want to do that. Double-ended queue. You always want to define your starting position and your ending position to find start and ending nodes. And these should be like the names of your node. So here in the list, in the dictionary, the names of my nodes are literally just numbers. So I've done the same thing here. Then you want to create the deck with the initial starting state. And remember, your state is always a tuple. Like every tuple represents a state. So over time, your tuple will be, there'll be more tuples in your queue. And then you want to always create visited set to save runtime, to save checking the same node more than once. And you're saying, while there are states to check, you always want to pop the leftmost state, and then you want to check, then you want to check if you've reached the destination goal, the goal. If not, then you want to check you've not visited this node before. And then this is like the actual algorithm bit, and this is where you're saying add every possible state to the queue, add every possible state based off my current state to the queue. So your current state is kind of just your node where you are, and you're saying where else can I go, and you're adding those states. So I mean, that's just a generalization of the code. I'll zoom out a little so you can see all of that. Hopefully that's big enough to see. And like, this is just really the core code. This is the core code you need basically every single time you're writing a BFS. And that you can adapt this so much. Like if you saw my video today, you'll probably see how different my code looked. But you can see it has all the fundamental ideas. It has this. It has a dictionary. It has this while loop. It has a visited set. It has this popping idea. So it has all the same things. And I think what you should do if you want to learn BFS properly is look through this code, copy it, play around with it, like really truly understand how it works, what it does. Maybe every time you go through here, maybe you want to print a queue, just so you can understand what your code is actually doing. And I recommend, if you get a really good understanding of your code, graph algorithms can be so powerful because they can be used for so many things. You can adapt this BFS into Dijkstra's really, really fast with like 2 lines of code if you truly understand this. And you can use this algorithm for pretty much everything if you truly understand it. Not everything, but like a lot of things. And so I'll take the time if I were you to like copy this, play around with the code, see what it does, maybe try and adapt it to a few other examples you find on the internet. But this is the fundamental code, that's how it works, and that's how I solved this solution. But in reality, like your state can contain anything in it. Whatever information you want to include, you can contain within the state. As long as you're consistent when you update the state and add new states down here, you can contain anything. Yeah, I think just really try and understand that idea. And once you do, you'll be a much better programmer and much faster at coding graphs. So, you know, hopefully this video is useful. I also don't want to give you too much information and too much help, because programming is about learning yourself, discovering things yourself, and truly understanding things by yourself. Hopefully this is just a starting point to help you do that. And hope you enjoyed. Yeah, thank you. And maybe if you're struggling with day 12, hopefully you can now do it. It might take you a couple of hours, but that's all good. It's all about learning the new techniques, learning the new ideas, and getting better and getting a stronger programmer. Like, I only learned this a couple of years ago when I did AoC. It took me so long, so long to do the puzzles. But after I learned this, it was so easy. So, you know, I'd recommend, even if it takes a couple of days, properly engross yourself in this algorithm. And once you get it, it's going to click. And you're going to be much faster at competitive programming. But anyway, yeah, thank you for tuning in. Hope you have a great day, and hope you enjoyed. So, bye, and see you for next time. Hi, it's Future Me. Just to remind you, the code will be down in the description down below on my GitHub repo. So check that out if you're interested. Yeah.